Okay, first I will start with some basics from information theory. So you see there a point-to-point connection from a source to a destination. So the source output could be, for example, a Chinese text or something, some voices spoken via telephone or something else. And this text, of course, have to prepared for the transmission system, which of course doesn't know the Chinese letters. So the text is translated, for example, in a sequence of binary digits. So the channel encoder now translates this binary sequence into a sequence over the input alphabet. We call it X here. If the channel is, for example, a telephone line, then the messages are transmitted in form of electrical pulses, and the alphabet size could depend on the possible pulse durations. The channel is usually noisy. The letter can be disturbed by the channel. And the channel decoder receives the sequence of letters over an input alphabet Y, which normally is not the same as X. Observe that they are not necessarily the same. This sequence is translated again in binary digits, and hopefully the destination will get the same text. So if you look at this picture here, then you see that we have different goals. So for example, the source and the source encoder, their goal is somehow to get out the redundancy of the text because they want to compress it. So in this here we have more or less, we have data compression. This is also called this area that's part of the source encoding. So if you look now at this part here of this channel, here you have a channel which is normally noisy. So the goal of the channel encoder is to put in some redundancy in such a way that the channel decoder can decode the sequence correctly, or also if there are errors here in the channel. So here we want to insert some redundancy. This part here, this whole part here, that's channel coding. Now if we look here further, then after this channel coding, he receives the sequence here without any redundancy, insert some redundancy and put it to the destination. So we have two areas. We have this area here. This is the area of source coding. And we have this area here. This is the area of channel coding. And as I told you, the goals are even different of these two systems. We will look at them separately. There's also some research on it because you can sort about, of course, we have already some redundancy in this example in the Chinese text, for example. Why couldn't we use this redundancy for the channel? And so we don't need these two steps, but there's a theory about this that for simple channels, or this is not gives no better result. So it's always the best way to analyze this is to look at source encoding and channel coding. So, and we will do this in this lecture, but of course we will use at multi-user systems. So again here you see, observe that the source encoder and the channel encoder have contrasting tasks. The source encoder wants to produce a short sequence of bits, so his concern is data compression, so remove the redundancy. And the channel encoder wants to assure that the message transmitted can be correctly decoded at the receiving end. So his concern is to build in redundancy to the sequence. Of course, what our goal is, so we will look in this lecture as at source coding models and at channel coding models. And here's an example which we will have at the very end. And you see, not as before, we don't have here one source, we have here three sources. And we don't have here one destination or thing, we have here two destinations. So you see, we will look at multi-user models. That's our goal. What is now an information theoretically analysis? So this theory is based on Chen, and you need probability theory and statistics. And the important tools, which I will also define, but most of you should know from the information theory course, that's the entropy, h of x. This is a measure of information in a single random variable x. And then the mutual information. This is a measure of information in common of two random variables, x and y. And those of you who have attended the information theory course knows that both of this play an important role in information theory. What we want to analyze is the so-called code rate. That's a proportion of the data stream. So you see here M denotes the number of messages over n. So we take the logarithm of the messages over n. This is called the rate. If you now think of a binary noiseless source, then you know that we can transmit 2 to the n messages. So then the rate is 1. And the capacity is the supremum of all achievable rates. And you know from your information theory course that the capacity of a DMC is equal to the maximum over all random variables x and the mutual information between x and y. And what is different? So in term information theory lecture, this result was proved with Gallagher's method. So what we will do, we will introduce also the so-called typical sequences. And we will give an alternative proof of this result. And the reason for this is that we can use these typical sequences also for the analysis of the multi-user channels.